afternoon, everybody. We start our third session on extreme light conference. And first talk will be given by Vladimir Fedorovich Kovalev, matching conditions for relativistic self-correcting flat of field.
Good afternoon to everybody, dear ladies and gentlemen. First of all, I would like to thank the organizing committee for giving me a nice opportunity to come to that institute. That's better. The title of my talk is well, what is not but spreading being. Of nonlinear equation that guarantees the propagation of light beam, of a powerful laser beam in a transparent plasma at a distance much larger as compared to the related length. Here is an example of such it is the realization in the form of the so-called bullet, the numerical calculation for a relativistic laser beam, localized plasma with a laser light inside. The result of such a steady propagation on 7 relay lengths in plasma is that the electrons that are self-injected inside this cavity are accelerated, and hence has many interesting possible applications. For example, secondary radiation nuclear applications and accelerator. And this is due, as a result of this, you can obtain the design characteristic for the electron beam with very high energy, high total charge, and low divergence of the electron. However, in order to realize this regime, it is not realized for arbitrary intensity of the laser beam, input laser beam, and its radius and the density of plasma, but there is a restriction, a so-called constraint, which, yes, that's better, which should be fulfilled in order to obtain this situation. It is the result of very many comparison of numerous 3D numerical computations with yet unknown coefficient alpha, which was calculated for in every particular case. It was different, but it differed from 1 to 2 or to 3, maybe that. So it's very interesting to check from a theoretical point of view. Is this matching condition true? Is it dependent on the beam intensity or on plasma density? Is this true or is it not? And what is in reality this coefficient that is usually obtained from the numerical calculation? So, in order to obtain, I should also point out that this condition is presented for the relativistic electron beam with a very large amplitude. What happens is, and in weak relativistic limit, how does this results compare with the strong relativistic case? All this may be obtained from the theoretical application. So in order to with we should come back to the second part of the 20th century, and we start with the works by Gaponov and Miller, and then followed by the work by Oskar Yankur and Ashotovich. In this work, it was stated that the charged particle would be expelled from the field of localization of the intense laser field. And as a result of this, the central idea how to obtain this the light beam which can propagate for a long distance in a waveguide manner. It is a situation that is may be realized if the nonlinear propagation of the wave beam changes the refractive index of the nonlinear medium in such a way that it compensates the geometrical and diffractional divergence. So is the power which can for this realization of such situation for the cylinder geometry was calculated a little bit later, and this is the minimum power which should be used for the cylinder beam. So this idea was realized in the later publications. Here I mentioned 3 of them by Talanov, which is for the plane beam, in which for the plane beam such localized configuration of the electric field is possible. It is in the form of the soliton beam, and you can see that the width of the beam is inversely proportional to the maximum amplitude of the laser beam. So for the cylinder geometry, it is the well-known Town solution for the cylinder beam, and the nonlinearity is also in the weak relativistic limit is simply a correction squared linear in intensity and square in amplitude, and again we have the localized beam distribution. And again, the same situation. The higher is the amplitude of the beam, the narrower is the beam. And the third work I mentioned it here because just to attach your attraction to the point that if you can, in an arbitrary manner, can help the beam to reach the so-called wave-guiding situation, for example, you may choose the focusing of the beam, but it is not the fact that it helps. There were examples in this publication that showed that the sharp of focusing simply destroys self-trapping, but not help. So it is also the question for the discussion. So these were the main results of the 20th century. And what happens if we now move to the 21st century? What is in the situation where the beam is relativistic intensity? So that means that we have the relativistic plasma. So the situation can change. This is the dimensionless beam amplitude. So we move from that limit to the limit when A is much greater than 1. So the main obstacles that you can meet on the way to self-trapping regime were observed only even in the initial works with the weak relativity. For example, the result of the experiment fulfilled by Pilipevsky and Rustamov, they observed the self-trapping regime, but in the trapped in the central part of the beam, only 1% of the beam power was captured. Only 1%. And what is more, that means that is the poor matching of laser beam, laser plasma parameters. This is not the cavity which I have shown you on the first slide. This is poor matching of the laser beam and medium parameters. And so several filaments were also produced in this first experiment. This is the second point I would like to attach your attraction. Instability. In general, you can meet two characteristic instabilities. This was, of course, observed for the relativistic beam itself, is so-called filamentation, when the beam is separated in different filaments. And in order to prevent this situation, you should have, for weak relativism, the radius which is less than this value for weak relativism. And in case of the strong relativism, you have a little bit weaker, not so strong equality. So the beam intensity helps to achieve the greater radius when the filament still does not exist. The same situation, the result of the numerical calculation, by Pukhov is presented in this slide. So again, we see the relativistic filamentation, which is fulfilled when this condition is satisfied. So if you take a beam of smaller radius, there will be no filamentation. Well, the next result, if you have the very long laser pulse, the next obstacle that you can came across is the longitudinal stratification of the laser impulse in a component which is also accompanied by a transverse ejection of energy. So if the beam is large in longitudinal direction, it is separated in 3 different parts, and only the leading part remains. It continues to propagate in the stable manner, and the other are destroyed. So in order to prevent the modulation and filamentation instabilities, the dimension of the beam should be of this, practically of the same size, not exceeding the laser plasma wave. The plasma is transparent, its density is small, so its value is much greater than the usual radius of the laser beam. And one more item I should touch upon is the following: that the radius of the focal spot should be inconsistent with the laser plasma density. This experiment by the Moreau and with co-authors just demonstrates the situation on the left panel. You see the situation when the beam propagates in a self-trapping manner, and on the right panel when the radius is much greater than the it's much greater the focal spotted rate, the laser pulse. So again, we come to the situation where we should prove, can we achieve this condition, how this condition can be obtained in the theoretical interpretation. So now I continue with the mathematical model. Of course, I can't, from the theoretical point of view, consider a situation where I have dependence on time, on the longitudinal coordinate zeta, so that, and I restrict myself to the situation of the quasi-stationary beam propagation. I just know the result of cutting the beam in the longitudinal direction and in the radius, in the transverse direction. And so I can consider the nonlinear Schrödinger equation for the quasi-stable beam. That means that I look for the configuration with this simple dependence on the z, and the nonlinear input is nonlinear permittivity, dielectric permittivity of the corresponding to the relativistic nonlinearity, which is presented in the form of the gamma factor. That means that we take into account the mass dependence of electrons, and the second is the situation which takes into account relativistic friction. When the laser pulse is strong enough, it evacuates electrons from the central region, and so the situation means that the density becomes lower, and even more, it can become negative in this situation. In this situation, there should be a correction. We believe that NE is 0 for negative values of n. This is one of the main contradictions in treating this model. So the cavitation zone is inside where the beam is localized for the high relativity. There are no electrons, and all these electrons are pushed in the outer region. But the situation is how to consider the boundary of this cavitation zone. There were several attempts to work by Borisov, Fate, and which is the work, the publication which is most important in the situation is the work by Kim in 2002, where it was shown that the conservation of the whole charge, of the total charge, should be taken into account, and this is the form of calculating the position of the boundary that separates the cavitation zone from the outer situation. And if we take this into account, this can be taking this representation into account. From this situation, we obtain the following additional condition which should be taken into account, which relates the constant, the phase constant gamma, it is related to nu, this presented here, with the relativistic factor on the boundary of this cavitation zone. As a result, however, even in this situation, this second order ordinary differential equation can't be solved analytically. It is a result of the numerical solution, but performing this calculation for different positions of cavitation zone, we, as a result, obtained the following. We obtain the following curve, which is well approximated, but this. So now there is no need to calculate, to make. Every time you can simply take the results from this numerical approximation. There is the result of the solid line is just this approximation, and the points are the results of computer simulation. Results of computer simulation. So now we can add the solution in the outer zone. It is also can't be obtained exactly in only numerical, but we simply get the approximate analytical representation for the solution in the outer zone. We use the result, this result, to find the position of the point, and here we just added this solution. And the difference between the real exact solid line and this line shows us the result of the approximation. It works very well. Practically, only for very small laser power, close to the critical power, the solution exists. We can use this approximate solution. These are the results of the intensity distribution for the laser beam, and the distributions, the density of electrons. You have this boundary well, just in the work by him, but they have only several points, and just to obtain this result for the whole curve, to matching condition, we use this situation. Now what's then? Now we're interested in, of course, in integral characteristics, the mean power and the mean radius beam are L. This is the result of the point is the exact following from the exact solution. This dashed line is the result of using or approximate analytical solution in this situation. Here are the results if that follows from the theory by Borisov and Fade. Just you see the difference between the type of the dependence of the beam radius on the amplitude, also on the power. And by triangles is just a situation if you simply omit the cavitation effect and simply use the dependence only on the gamma factor. What is surprising, the result from the exact solution is very little, not more than 15-20%. It's a very good accuracy, however, what is very correct. But this is the result found from our calculation. And for large values of P or what is the same for large values of laser amplitude is presented on this slide, P and A, and this is the asymptotic solution. The result can be found in this well. The same can be done for the weak relativistic case. I will not go in detail here. It is very it's common to the solution which is obtained for the top beam, and as a result we obtain the dependence on the parameters in the weak relativistic limit. And the next how to present, how to combine these results. So these are the results that you, if you place them on the full scale for large values, and especially what is interesting for the values just inside when the solution for large p's and for small p equal to 0. This is the only small narrow zone which we don't have analytical representation. Practically everywhere outside we have the analytical representation. To compare, this is the result obtained by Nasseri. We have a reasonable agreement with his results, but for large p's, the results suggested by Nasseri from numerical computation gives the wrong dependence on p. Okay. Well, what's that? And 3 or 5 minutes. So for the experimentator, it's much more useful not to have analytical but still not so simple formulas. It's much better to have some interpolation dependencies. These are presented on this slide. We have the asymptotic for large values of laser intensity, for small values of laser intensity. Then we add the smoothing function, f depending on p and k, and present you the result which you can find here. Correlation between theoretical numerical results and theoretical interpretation is given by this formula. this can be also done for the dependence upon P and upon laser intensity null. And as a result of this, we have the final formula, which may use as a so-called a cornerstone in the whole building of theoretical multiplication, and can be used in preparing the numerical simulation. Using this formula, you can choose the right values of critical density, the large values of laser power, and all other situations to be close to this self-trapping regime. That can be used. The result of such an instructive application is presented on the next slide. Just for example, this is a laser bullet. These guys of this self-trapping for different values of input power, input radius, and so on. Well, this is not the result of this work. It's simple an illustration. And the final slide is just where the result of this theoretical application, it is a central part of this scheme, where it can find where it can be used as an application. You can, in details, you can read about these applications in the following publication. Thank you for attention.
Can you determine the physical regulate the longitudinal size of the
Yes, of course, it's the so-called modulation stability with the size of the participation is of the root of the plasma wave excited during this instability.
Okay, in your simulation, this size.
No. We in our not simulation, in this simulation, yes. What's shown on
My
the
question is, which correlation
the model
between wavelength and the longitudinal size of
it just it just was the foundation of the model that we suggested. But of course, from mathematical point of view, we start with the model of the quasi-stationary laser beam. We know in reality we have these long laser pulses. It will be separated small pulses, but the transverse dimension is in good agreement with our theoretical prediction.
Very quick question. So you have bubble with light inside.
Yes.
Which velocity of the bubble propagation?
Nearly very close to light speed, to light velocity.
Very close or not equal?
Well, of course not equal.
So you decelerate light?
No. It disappears in intensity because it lost energy to form this cavity and to evacuate electrons on his way.
Okay. Let's stop discussions later. Okay, we have no time. Okay, next talk. Thank you very much again.